Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Henri Becquerel's 1903 Nobel lecture, titled On the Radiation of Uranium and of Some Other Substances, represents a foundational document in the history of physics, a personal testament delivered at the very dawn of the atomic age. In this address, Becquerel provides a meticulous, first-person narrative of the sequence of experiments and deductions that led from an investigation into phosphorescence to the discovery of spontaneous radioactivity. The lecture is a unique artifact, capturing a moment of profound conceptual transition, where the classical world of immutable elements and conserved energy was beginning to yield to the strange, powerful realities of the subatomic realm. This essay will undertake a direct and rigorous evaluation of the lecture's internal claims, proceeding section by section through Becquerel's own recounting of his intellectual journey. The analysis will focus on the validity of his experimental evidence, the logic of his inferences, and the evolution of his conceptual framework as presented within the text itself, revealing a mind grappling with a phenomenon that would ultimately dismantle the very foundations of 19th century physics. Section 1: The Initial Investigation and the Phosphorescence Hypothesis. Becquerel commences his lecture by framing his initial experiments within the established and familial expertise of phosphorescence, the emission of light by a substance after exposure to an external energy source. His central claim in this preliminary phase was that certain uranium salts, specifically potassium uranyl sulfate, after being energized by sunlight, would emit a penetrating radiation capable of passing through opaque materials like black paper and exposing a photographic plate. The methodology he describes is one of elegant simplicity. A photographic plate was wrapped securely in thick black paper, the phosphorescent uranium salt was placed upon it, and the entire assembly was exposed to sunlight for several hours. Upon development, an image of the crystalline salt was observed on the plate. His initial conclusion, presented as a logical extension of known physics, was that the solar energy absorbed by the uranium salt was being re-emitted as a form of hyperpenetrating, invisible light, akin to the recently discovered X-rays. The evidence he presents for this claim is the clear fogging of the photographic plates, which directly correlated with the position of the uranium crystals. The argument appears sound, linking a known cause, solar radiation, with an observed effect through the mediating property of phosphorescence. This interpretation, while ultimately proven to be a coincidental correlation, demonstrates a commendable adherence to the scientific principle of extending existing theories to explain new observations, for proposing revolutionary new principles. It was a perfectly reasonable, even expected, starting point for a physicist of his time and training. Section 2: The Anomaly of Spontaneous Emission and the Redefinition of the Source. The narrative pivots on a moment of pure serendipity, a detail that Becquerel recounts with an air of scientific humility. He describes preparing an experiment on February 26th and 27th of 1896, but due to overcast Parisian skies, the uranium salts received no solar exposure. He stored the prepared photographic plate and the uranium salt together in a dark drawer. Upon developing this plate some days later, purely as a matter of thoroughness, he found the image to be intensely clear. This leads to the lecture's first revolutionary claim: the radiation emitted by the uranium salt is a spontaneous and persistent phenomenon, wholly independent of any external excitation like sunlight. The evidence for this is the powerful photographic effect produced in total darkness. He then details his follow-up experiments, which systematically eliminated external energy sources. He kept samples in darkness for months, finding their emissive power undiminished. He tested uranium in various chemical forms, both phosphorescent and non-phosphorescent, and as a pure metal, leading to his second crucial claim in this section: the radiation is an intrinsic atomic property of the element uranium itself. The intensity of the radiation, he argues, is proportional to the quantity of uranium present in the sample, a finding that moved the phenomenon's origin from a molecular property like phosphorescence to a fundamental atomic one. His evaluation of this evidence is incisive. He correctly deduces that he has stumbled upon a new property of matter, one where an element continuously radiates energy from an unknown internal source. This section of the lecture marks a conceptual birth of radioactivity, moving decisively away from the phosphorescence hypothesis toward a far more profound and perplexing reality. Section 3 Characterization of the uranium rays and their properties. Having established the existence of this spontaneous radiation, Becquerel next details his efforts to characterize its physical nature. The central claim of this portion of his lecture is that these new rays share properties with both light and X-rays, specifically their ability to ionize gases and their supposed capacity for reflection, refraction, and polarization. His primary evidence for the ionizing property is the discharge of a charged gold leaf electroscope, where a uranium compound is brought near, a method that would become a standard for quantifying radioactivity. This observation was robust and repeatable, correctly identifying a key physical effect of the emissions. His claims regarding the optical properties, however, are more complex. He describes experiments where he attempted to reflect the rays from a mirror and refract them with a quartz prism, reporting faint but positive results. He also claims to have observed slight polarization by passing the rays through tourmaline crystals. These claims represent an attempt to assimilate the new phenomenon into the well-understood framework of electromagnetic waves. In retrospect, the evidence he presents for these optical properties was likely experimental artifact. The effects he observed were at the very limit of detection and were later shown to be incorrect for the bulk of the radiation. This highlights a critical aspect of scientific discovery, the powerful influence of existing paradigms. Becquerel interpreted his faint, ambiguous results through the lens of what he expected to find, a form of invisible light, while his specific conclusions about refraction and polarization were erroneous. His methodology of systematically testing for the known properties of radiation was sound, and his correct identification of the ionizing nature of the rays provided the first quantitative tool for their study. Section 4 The discovery of other radioactive substances and induced activity. In this section, Becquerel broadens his scope to incorporate the rapidly unfolding discoveries of his colleagues, particularly Murray and Pierre Curie. He fully credits their work, showing a remarkable lack of possessiveness over the field he initiated. The primary claim is that the property of spontaneous radiation is a feature of other elements, specifically thorium, identified by G.C. Schmidt and Marie Curie independently, and the far more active elements, polonium and radium, which the Curies isolated from pitchblende. He presents the evidence for this claim by citing the Curies' electrometric measurements, which showed that the activity of pitchblende was greater than could be accounted for by its uranium content, leading them on their heroic search for new elements. A second major claim in this portion of the lecture is the existence of induced radioactivity. Becquerel describes how normally inactive substances, such as lead or glass, become temporarily radioactive after being exposed for some time to a higher active source like radium. His evidence is that these on-inactive materials could then discharge an electroscope on their own, a property that decayed over time. He correctly interprets this as a transport of activity from the source to the object, though the mechanism, which we now understand as contamination by gaseous radon and its solid decay products, was still a mystery. This part of his address demonstrates his ability to integrate new, complex data from other researchers into his evolving understanding. He confirms their findings, grapples with the astonishingly high activity of radium, and correctly identifies the phenomenon of induced activity, all of which pointed toward a process of immense complexity and power far exceeding his initial observations with uranium. Section 5 Unraveling the complexity of the radiation through magnetic deflection. The intellectual climax of the lecture arrives as Becquerel discusses the influence of magnetic fields on the rays. This section dismantles the earlier, simpler model of the emissions as a singular type of ray. His central claim is that the radiation from radioactive substances is composite, consisting of at least two distinct types. He describes experiments, building on the work of Giesel, Meyer, and Villard, where the rays are passed through a strong magnetic field. The evidence is striking. A portion of the radiation is deflected, following a curved path indicative of charged particles, while another portion is undeviated. He further claims that the deviable rays are identical in nature to the cathode ray corpuscles, or electrons, discovered by J. Shea Thomson. The evidence for this is his own quantitative analysis of the deflected rays from radium. By simultaneously applying electric and magnetic fields, he aims to correlate the velocity and, crucially, the charge-atomical of these particles. He states that the velocity is exceptionally high, approaching that of light, and that the calculated ratio of the particle's electric charge to its mass is on the order of 10 to the power of 7 electromagnetic units. This value, he triumphantly notes, is the same as that determined for the electron. This is a masterful piece of experimental physics, and his conclusion is entirely correct. He names these negative particles beta rays. He also acknowledges the existence of a more penetrating, less deviable and non-deviable component, which Rutherford would later christen alpha rays. Becquerel's argument here is powerful and conclusive, supported by quantitative data that links the phenomenon of radioactivity directly to the newly emerging subatomic physics of the electron. He successfully transforms the understanding of his rays from a vague, light-like emission into a stream of actual matter ejected from the atom at incredible speed. Section 6. The profound question of the energy's origin. In the final substantive part of his lecture, Becquerel confronts the most profound and unsettling question raised by his discovery: the source of the seemingly inexhaustible energy of radioactive substances. He makes a claim that is less a conclusion and more a carefully framed statement of a fundamental problem. He posits two possible, and radically different, conceptual frameworks to explain the energy. The first hypothesis is that radioactive atoms act as intermediaries, capturing some unknown, highly penetrating radiation from the cosmos and re-emitting it, thus preserving the conservation of energy and the stability of the atom. This was a conservative explanation, an attempt to keep the phenomenon within the bounds of classical physics. The second, more revolutionary hypothesis he presents is that the energy originates from within the atom itself. This implies that the atom is undergoing an internal transformation, that it is mutable, and that the energy released is a consequence of a change in its very substance. He cites the Curry's astonishing measurement that radium continuously emits enough heat to melt its own weight in ice in about an hour as powerful evidence for the magnitude of the energy involved. He presents these two hypotheses without definitively choosing, yet the weight of his discussion leans towards the second, more radical idea. He speaks of the atom as a complex system and the radioactive emission as a projectile coming from within, suggesting a dislocation of the atomic structure. This claim, that the atom itself might be the source of the energy through its own disintegration, was the most forward-looking statement in the entire lecture. It directly challenged the millennia-old concept of the indivisible, unchanging atom and set the stage for the nuclear physics of the 20th century. His intellectual courage in articulating this possibility, even as a tentative hypothesis, is perhaps the most significant aspect of his entire address. He identifies the core mystery that would lead directly to Einstein's formulation of mass-energy equivalence. Conclusion: Henri Becquerel's 1903 Nobel lecture is far more than a simple summary of a discovery. It is a live-fire account of the scientific method operating at its highest level. In evaluating its claims section by section, one observes a narrative of intellectual evolution, from a plausible but incorrect hypothesis rooted in classical physics to the reluctant embrace of a new and revolutionary reality. His initial claims about phosphorescence were logical but disproven by his own meticulousness. His subsequent claims, identifying the radiation as a spontaneous, atomic property of uranium and its ability to ionize gas, were fundamentally correct and established the groundwork for the entire field, while his assertions about the optical properties of the rays represented a temporary misstep, a product of experimental difficulty and the allure of existing paradigms. His later work, presented with quantitative rigor, correctly identified the beta particle as a high-speed electron. Most importantly, his concluding speculations on the origin of radioactive energy demonstrated a profound grasp of the discovery's implications, framing the central question that would define the physics of the next generation. The lecture captures a snapshot of a great mind at the boundary of the known world, honestly reporting experimental successes and failures, and boldly articulating the questions that his own work had unleashed. Its enduring value resides in its faithful portrayal of a paradigm in the process of being born, a process of shedding all certainties and confronting a universe more complex, more powerful, and more mysterious than previously imagined.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.